So when I consider one-dimensional problem, so make sure the cross section, right? So we always consider the cross section as a overall value, right? For a beam, if I need what is the cross section, so what we will do is we will consider moment of inertia I as a cross section. Okay, so this is applicable for beam, right? So why I am using this I? Because the stiffness matrix formula will be in terms of EI by L cube. Okay, so you have I. So similarly, if you consider bar element, right? So we consider the cross section, area as the cross section. So only if you know the value cross sectional area, I can able to understand, because our formula will be in terms of AE by L. So we are converting, actually what we are doing is we are converting a three-dimensional figure into a one-dimensional figure. So what we are going to do here is we are going to consider this three-dimensional figure to two-dimension, right? So when I go for two-dimension, there are some differences, right? Because the size of the element and other things are varying, right? 1D it is similar because it's just a line. But if I go for 2D, your element may be a triangle, maybe a rectangle or a square, right? Of course, it may be also be hexagon, something, trapezium. So there are lots of variant of your two-dimensional elements, right? Everything is two-dimension, right? So that comes under complications. So now what we are going to do is we are going to deal with a triangular type of element. We start with triangular element, then we'll slowly go for square elements. So you can able to say that you consider a problem in a 2D plane, right? It may be a gear tooth analysis. So you know that, so if there is a contact of gears like this, so something like this, right? So what will be the stress formed in this location? A gear tooth analysis or a hook analysis. If I consider a hook, something like this. So varying cross section. Okay. So for this hook, so when you apply a force, what happens? What is the stress developed in this hook, right? All these things, when you look in 3D, it is different. When you look in 3D, it is different. But what we are considering, we are converting that 3D to a two-dimension, right? So, and we are solving it. Okay. So your two-dimensional element, it may be a different types of elements. Minimum, it requires three nodal points. Minimum, you require three nodal points. So other than this, you can also have 4 or 5, 6, 8 accordingly, right? So these are from few examples of two-dimensional elements. This is a triangular element, which is having 3 nodes. This is a quadrilateral element, which is having 4 nodes. And of course, you can also include few more nodes here, which will be a different type of approach, right? That is, this one is related with a linear element. So when I include one more nodal points in between, we call that as a cubic element, okay, or something like that. Okay, so these things are different elements. So you can able to see how this elements is distributed in your two-dimensional plane. So you can able to see it's like a connecting rod. You can able to identify shape as a connecting rod. All the shapes is converted to a triangle. So you can able to see small pieces of triangles, right? Each piece of triangle is one element. So if I consider here, this is element 1. So element 2, element 3. There are lots of elements here. Okay. So what happens here is, so for example, if I consider this part, okay. So let me consider this part. So there is a force which is acting here. So this force vector, right, is transferred. So this two force vector will be transferred to the other nodal points, right? It will be transferred to the other nodal points. And for example, if I apply this force, what will happen to this? So this will deflect, right? So that force will be considered for this particular element, and it will go on, right? So this is how it will transfer your data from one point to the other point. Okay, so that you can able to get a overall structure of the element. Okay, so these are all comes under two dimension. So this two dimension is classified into three different types. So one we call it as a plane stress. The other one is plane strain. The last one is axisymmetry, right? So this axisymmetry we will discuss it later. First, we will discuss about what is plane stress and plane strain. So this two different types of element indicates how to convert a three-dimensional figure to a two-dimensional figure, right? So let me consider here. So a plane stress, as the name indicates, you have stress only in this plane, in a plane. You have stress only in the plane. That means you may have a stress in xy and your z may be 0. Or if it is in other dimension, you may have it in x, y, z and your x will be 0. Right? This we call it as a plane stress problem. Right? A state of stress in which normal stress and shear stress perpendicular to the plane is 0. Right? So this is the, you can able to see here, this is the statement, a state of stress in which the normal stress and shear stress directed perpendicular to the plane. So when I say perpendicular, if I consider xy plane, perpendicular plane is z plane. In that plane, your stress is 0, right? So that we call it as a plane stress problem, right? So how you identify a plane stress problem? When the thickness of the material is lesser, then we call that as a plane stress problem. Okay, so the member thickness is very, very less, right? That we call it as a plane stress. You can able to see here. So you have a figure here. So when I consider this, the thickness here is very, very less. So thickness is very less. Then we can consider this as a two-dimensional problem. In which category? In plane stress category. Okay. So in this, you can able to see that your sigma z. So stress in z direction is 0 and shear stresses in z directions. So tau xz and tau yz are also 0, right? It comes under plane stress condition. So let me consider here. So if I want to analyze a frame like this, right? So in 2D, what I will draw? I will draw this rectangle. I will draw this rectangle because the thickness is very less here, right? So I can consider this as a plane stress problem, right? I can easily solve this in a plane stress category. So similarly, let me consider here, you have something like a hook, right? So you see that the dimension of the hook is something like this, and the thickness of this is only 5 mm. It is mentioned here, right? So what I can say, I can just draw this hook cross section, just the hook cross section, and I can able to analyze this, right, in plane stress condition. So this also comes under plane stress condition. So the next one is plane strain. Right, as the name indicates, your strain is only in your plane, which means you have strain only in x direction, you have strain only in y direction, and you don't have strain in z directions. Okay, that is plane strain problem. So you see like this, you can able to see that the thickness is very, very large when compared to your normal section, the front view. Your front view is less, but your side view, if you see, your thickness is very, very large, right? So that one we call it as a plane strain problem. Okay. So what is the statement? The state of strain in which normal strain and shear strain normal to the plane. So normal strain and shear strain normal to the plane are assumed to be 0. That is what we say that strains in z directions are 0, right? So it is always considered if you have a large number of thickness. So when the thickness is very, very large, when compared to your x and y, right? Then we consider this as a plane strain problem. Okay. So here you say that your strain in z direction is 0 and strain, so gamma xz and gamma yz is also equal to 0, right? So this comes under plane strain condition. Let me see here. So you want to analyze this cuboid, you consider this plane. right? If I consider this plane, so Z direction, you have a very, very large thickness, right? In that case, if you want to analyze this, you can consider by using plane strain. So this can be solved by using plane strain condition. What happens if I take this as my cross section, which means I am drawing this rectangle? Which condition is this? Anyone? Right, it comes under plane stress condition. Very good. So look here. So this also. So you can able to see that you have a tank here, something like this, right? So what I can do, I will concentrate on this part, right? When I concentrate on this part, so I'm going to draw this part, right? So you will get something like this, right? So something like this, right? So make sure so your thickness is 180 mm when compared to your hip, other things, right? So what happens? This comes under plane strain condition. This also comes under plane strain condition. So what are the other problems? Look here, you have a weld joint, right? So let me consider you have a T joint, something like that. You are welding it. So I'm going to concentrate on this welding part. What is the stress developed on this welding part? Right, so if I draw, it will be a small triangle like this, a small triangle like this. Okay, so but what is the thickness? So the thickness of the triangle is very, very large, right? It is very large. So you can solve this by using plane strain condition, right? So that is another part. Okay, so this is the overall differences. So when I talk about axisymmetry, it is a revolved object, right? So whenever you want to solve a problem of a pressure vessel, right? So you can able to see that it is like a cylinder. So you consider the cylinder as a rectangle and solving it. That is axisymmetric problem, right? Anyway, we will discuss it later. Okay, let me consider. So this is my CST element. So this element is having three nodal points. So nodal point 1, nodal point 2, and nodal point 3, right? So when you write it in an equation, so you can able to see you have only three nodal points, which will be a linear type of element. What do you remember linear? Linear means your power is 1, right? So x power 1, something like that. So you look after this. So this is related with x-axis and y-axis. So if I write my trial function, your trial function will be like u is equal to a1 plus a2x plus a3y, right? Because in terms of x and y, it is linear, so it should be in terms of x and y. Okay, that is my trial function. So you consider that this is my displacement. So u1, u2, u3, v1, v2, v3, and you can write u as your trial function, which is with respect to x-axis, which is a1 plus a2x plus a3y, and v is a trial function with respect to y-axis, which is a4 plus a5y, sorry, a5x and a6y. How you are identifying this x, y, something like this? What happens if there is some other points in between? You know that for a one-dimensional element, if I consider a one-dimensional element, so the trial function what we consider is u is equal to a1 plus a2, a2x. So it means that it is power 1, it is linear. The problem, it's a linear type of element. So if I need to expand it, increase its accuracy, right? There is another way. So you can go for quadratic element. So quadratic element will have additional node 3 in between your other two nodes, right? In that case, what you will do, we will consider u is equal to a1 plus a2x plus a3x square. This is what we will consider, right? So we are increasing the polynomials accordingly, right? So, but in CST, so you have x and y. So how to do that, right? How to increase that polynomial? So if I need more number of nodal points, right? So for that we use Pascal triangle. So we use Pascal triangle to identify that. Okay. So note that, so there is no polynomial degree, which means 1. That is enough. That you leave it out. So if I want a CST element, let me consider this is my CST, which is having only nodal points on the corners, right? So you need 3 terms. You need 3. What is your polynomial degree? 1, which means you will get x power 1, y power 1. So what you have to do is you have to consider your polynomial like this 3. So this is what we write it as a1 plus this one, a2x plus this one, a3y. So this is my u, right? So if I need more degrees, for example, let me go for this LST element. LST is linear strain triangular element, right? So it has nodal points in between the corners. So even in the midpoints, you have some nodal points. So this is one element, right? So you have 6 nodal points. You have 6 nodal points, and your polynomial degree is x square. In that case, what I have to do, I have to consider up to this. This is my triangle. So how to write the triangle function? It should be written like this: a1 plus a2x plus a3y plus a4x square plus a5xy plus a6y square. This is my triangle function u of x. Okay, so this is how it will increase. So if you go for higher degrees of polynomials, right? But you no need to worry more than that. So you consider only CST, which has only these 3 terms. Okay, not more than that. Okay, so these 3 terms can be used to solve problems related to that. So because there are 2 methods, one, as we discussed earlier, we have something called as H method, and we have something called as P method. So P method is increasing the polynomial, H method is increasing the number of elements. So the best option is increasing the number of elements. So we prefer CST element instead of LST or QST elements to solve any problem. So instead of going for midpoint nodes. Okay. So then you may ask why we are using this. So it can be used only on corner nodes. So for example, if you have a fillet, right, something like this. So let me consider you have something, a curve like this. Okay, I have to fit this curve, right? I have to fit this curve. So how to do? So if I consider my normal element, what happens? Your normal element will consider this as a triangle like this. That's it. Okay, that is your CST element. But what happens if you consider LST element? There is a possibility that your element will go like this, right? You can create an element like this. So because of the center nodal points, you may have more convenient to change its shape, right? So there you can use these types of things. Okay. So that is another part. Okay. So, but we'll go for the CST. So in this CST, let me consider you have a displacement in x direction. So you have 3 nodal points. So each nodal points is having u1, u2, and u3. Right? So each nodal point is having u1, u2, and u3. So if this is my nodal point, so I will call it like this. So say a1, a2, a3. I am writing this as a matrix form. My aim is to identify this a1, a2, a3. Right? What I do, I have to take inverse. So I have to bring this on this side. Right? So let me call this as D matrix. So to identify what is the inverse of D matrix, I have to identify what is the cofactor for D, and I have to divide by its determinant. So D inverse is cofactor transpose divided by determinant. So how to identify the cofactor, right? So cofactor for C11 for this. So you eliminate this two. So you consider only this thing. So x2 y3 minus x3 y2. Cofactor for C12. You consider y3 y2. Right? So minus of y3 and y2. So you identify something like this. Each cofactors for C11, 12, 13, 21, 22, 23, 31, 32, 3. All these things, you write it as an equation, then put a transpose of this, identify what is the determinant for your D matrix, then you will get something as a D inverse matrix. Okay. So you'd see the determinant is like this. So what I say, if I consider the area of a triangle, your area of the triangle is half of this particular matrix, what we consider. So which means you can able to see this and this values are same. So which means I can say that your D matrix is nothing but your area. Your D matrix is nothing but your area. So half of your area, right? So which means I can write it like this, right? So A1, A2, A3, 1 by 2A of remaining terms. So since it is very complicated, I will give a new name, which is P1, P2, P3, Q1, Q2, Q3, and R1, R2, R3. So some books, the notation will be different, but the concept is same. So it is relating your coordinate points, right? It is always relating your coordinate points. What is P1, P2, P3? So that is what this equation. So x2, y3 minus x3, y2. So similarly, q1 is y2, y3. So these are the terms. Now, so consider what is my U matrix. So what is my U trial function, which is a1 plus a2x plus a3y. I'm writing in a matrix form. So this a1, a2, a3 is what we identify now. So I am replacing it. So this a1, a3 is 1 by 2a of p1, p2, p3, q1, q2, q3, r1, r2, r3 in terms of u1, u2, u3, right? So I am replacing it like this. When multiplying these things, you get an equation. This is related to your equation n1, u1, n2, u2, and n3, u3. What is this n1, n2, n3? So this we call it as interpolation function, right? So similar to what we discussed earlier. So this is interpolation function. Okay. So which means I can identify this term is n1, this term is n2, this term is n3. So replacing it, I am writing it like this as a formula. So n1 is p1 plus q1x plus r1y divided by 2a. n2 is p2 q2x plus r2y divided by 2a, and similarly m3. Right, so these are my interpolation functions. So this can be used if you want to identify the values in between. Now, let me go for my derivation. This we already discussed. So you have force vector, so you have force and your displacement. It can be related. Similarly, stress and strain. So if I want to relate your stress and your strain and displacement, you can put d by dx. Right? So what is this d by dx? Is nothing but your B matrix. Similarly, relating your stress and strain it is your Young's modulus. Now your Young's modulus is different because it is in 2D, right? So this one we call as a D matrix, right? So you have a matrix which is D matrix. Then relating F and your stress, right? It is opposite of your B matrix, right? So in that case, you can relate what is these things that we call it as a K, right? What is your stiffness matrix? So we identify. So what is your stress? What is your strain? And what is your stiffness matrix? So we identify stiffness matrix as B transpose dB. Like same thing what we discussed in your one-dimensional elements. My aim is to identify what is this B matrix and D matrix. Your B matrix is strain displacement matrix. So note it is strain displacement matrix. That is your B matrix. Okay. We will discuss it in next class.